Welcome back, everybody. Learning as a hobby here, and I want to get back around to Spivak. I've been in the mood to get around to chapter 5, so I started on that today, and this video is going to be the summary for chapter 5. This was kind of a long chapter, so actually, what I suggest you do is, because in my summary it's so long, I couldn't fit everything in there, and it's really most of the book I'm finding out is very conversational. So if you are interested in the material that's in this section, you should definitely read it yourself, because there's not I don't go over everything that he talks about in the chapter in my summary. It's just too much to do. There are also a lot of exercises in this for this chapter, so it's going to take me a while to get through the exercises there, but I should have that video posted at some point this week. So I'm going to try to catch up a little bit on the 5 books that I've been working on for a while. So if you saw my last video, I said I'm going to try and post a video, at least one video every day for the next couple of weeks at least. So let's jump into it. It's been a while since we've done Spivak, so let's jump into chapter 5, which is going to be a fun chapter because it's the beginning of calculus. So let me bring up my notes. Okay, so like I said, there's way too much stuff that he talks about in this chapter for me to, include it all in my summary here. So I just really did the highlights, wrote down the highlights of the chapter. So he starts with a provisional definition of what a limit is, which I have written here. The function f approaches the limit L near A if we can make f of x as close as we like to L by requiring that x be sufficiently close to but unequal to A. So what we want the notion of a limit to do is to capture what it means for a function to be getting close to a point in the range when you get close to some point in the domain, but not necessarily at that point in the domain. So it's giving you the behavior in a neighborhood of the domain around a point. So that's what we want the notion of limit to capture. And this whole chapter 5 is on limits. So this is the provisional definition. And then let me just say, he has a whole discussion after this provisional definition where he gives motivation for the formal definition of a limit. You should definitely read that section, read that part of the chapter, because I don't have it included here. It's just, like I said, it's just too long. So from here, I jumped right into, let me scroll down, right into the formal definition. So like I said, it is worth reading that part of the chapter where he motivates this definition, because it can be kind of jarring the first time you see it, because it looks very complicated. Let me read it out for you. The function f approaches the limit L near A means, so this is the definition, for every epsilon greater than 0, there is a delta greater than 0, such that for all x, if 0 less than absolute x minus a less than delta, then absolute f of x minus L is less than epsilon. So this formalizes what the provisional definition was trying to get at. So in other words, if we get close enough to A in the domain, we should be able to get close enough to L in the range. So that's what that provisional definition was getting at. Here, this gives the exact meaning behind what we mean by sufficiently close and so on. And also the fact that this is greater than 0 means that we are not considering what happens when x is equal to A. So we don't actually care what happens at the point A. We care what happens in a neighborhood around A in the domain. All right. Now, after he goes over the provisional definition, like I said, he gives a nice motivation of where this definition comes from, and he does that by doing a number of examples, which, like I said, I haven't included here because it's just too much. But after he gives the formal definition, he says, oh, remember all those examples that I just showed you? Do them now with the formal definition. And he doesn't do it in the textbook. He says you should do it. So that's what I decided to include instead of his motivation paragraphs. So he doesn't show these in the book, but he says do them. So these are all my proofs that I did because he says to do it. So before I do that, though, it is important to know the negation of the definition of limit. And that's because sometimes you want to show that the limit isn't some number L. So for example, if limit x goes to a of fx is not L, what this means is there exists an epsilon greater than 0 such that for all delta greater than 0, there exists an x such that 0 less than absolute x minus a less than delta, but f of x minus L greater than equal to epsilon. I don't have this really memorized. I mean, I know what it at this point in my life, I have this definition internalized, so I don't really have to like memorize it. I just know what the limit means and how to use absolute values and inequalities, and I just know how to write it down. But if you're just getting used to this, these definitions, and you're kind of, iffy on proofs, it would probably help to write these out in symbols. So for example, I didn't write this here, but let me just do it for you so you can see what I mean. For the definition that I have written above, you could write that like this. For all epsilon greater than 0, there exists delta greater than 0, such that for all x in the interval from let's see, I guess I could write it as an interval like this, a minus delta, a plus delta. I'm just trying to think if I want to write it that way. For all x in that interval, or should I write it as, I should probably write it as an implication. Hang on. For all x, let's do it like this. For all x in R, if 0 less than absolute value x minus a less than delta implies absolute f of x minus L less than epsilon. So this is the written out, in the logical, symbolic logical form. So here, if you wanted to negate this, it should be easy to do it, if you have it written out symbolically. So if you negate this, you get there exists epsilon greater than 0 for all delta greater than 0. There exists x in R such that 0 less than absolute x minus a less than delta. And you got to be careful about the negation of an implication. The negation of a conditional is a conjunction, not another conditional. So be careful about that. So here this would be 0 less than absolute x minus a less than delta, and maybe I should put these in parentheses so it's clear what things are part of the conjunction. And f of x in absolute value minus L greater than equal epsilon. All right, so it's, if you, this is logically, these two statements are logically equivalent. So, if you write it out symbolically, if you're, like I said, if you're just getting used to these definitions, this can help in negating the statements. So he doesn't go over this in the book. It's just something that I suggest that you do if you're not so strong in proofs at this point. So anyway, like I said, what he does is he says, those examples I did before, do them with show that they work. Approve the statements using the formal definition. So he does a couple of examples with linear functions. So I decided to just do it in general for the first example. So let's say that the line is not vertical or horizontal, so that the slope here is not 0 and it exists. It's a number. So that meaning the line is not horizontal or vertical, right? Then I want to show that the limit as x goes to a of mx plus b is ma plus b. All right, so when you're doing these proofs, you have to do some scratch work to figure out what delta is. That's basically where all the work is. So here I start with what I want, which is I want this thing to be less than epsilon. So I want the difference f of x minus L in absolute value to be less than epsilon, right? Here, if I simplify the expression in the absolute value, I get absolute value m times absolute value x minus a, and m is just a number, right? So I can and the x minus a in absolute value is the thing I want to bound above by delta. So here this says that absolute value m times delta, that's what I want to be less than epsilon. So I'll choose delta to be less than that number epsilon over the absolute value of m. And then it's just a proof showing that the function satisfies the definition for the limit. So here's the proof. Let epsilon greater than 0, choose delta less than epsilon over absolute value m. If 0 less than absolute x minus a less than delta, then consider f of x minus L, right? So absolute mx plus b minus, in parentheses, ma plus b. When you simplify that, you get absolute m times absolute x minus a less than absolute value m delta. But delta we said was less than epsilon over absolute m, so this is less than absolute m times epsilon over absolute m. And notice that the absolute m's cancel, which leaves you with epsilon. So that shows that the definition is satisfied. So that proves that the limit of this linear function is ma plus b. Okay, same. And then I did a similar thing for general quadratic. Well, I didn't choose a general, the most general, like I didn't choose a coefficient for x, but you could get around that, because you can factor out the the constant a out in front, and then the limit here will still work. But anyway, I want to show that the limit as x goes to a of x squared plus bx plus c is equal to a squared plus ba plus c. So I'm doing this in general. So again, here's the scratch work. I want to, start with what I want. So I want x squared plus bx plus c minus a squared minus ba minus c to be less than epsilon. So simplifying this expression here, I get this when when I'm completely simplified and then factored, you get absolute x minus a times absolute x plus a plus b. Now, the x minus a is what I want to bound above by delta, but I get this annoying non-constant factor here. So I have to, in order to get around that, he discusses this in the chapter, by the way, in order to get around that, I need to choose an actual upper bound for x minus a. So let's say that x is minus a is less than 1. So we can, you don't necessarily have to choose 1. You could choose, 1 over 10 or 1 over 100 or 1/2 or whatever you want. You just have to find some upper bound for x minus a, a fixed upper bound for x minus a. So I chose 1 just because it's an easy number. And it really doesn't make that much of a difference for quadratic functions. Of course, you don't want to choose it too large because you're trying to focus in a small neighborhood around a. So you don't really want to choose it to be too big. But here I'm just choosing 1 in general. So that means that x is between a minus 1 and a plus 1. And if I multiply through by, if I add a and add b to all 3 sides of that inequality, you get 2a plus b minus 1 less than x plus a plus b less than 2a plus b plus 1. And that means I can choose 2a plus b plus 1 to be an upper bound for that other factor. So x minus a in absolute value times x plus a plus b in absolute value will be less than absolute value 2a plus b plus 1 times delta. Okay. And that's what I want less than epsilon. So then all I have to do then is choose delta to be the minimum of either 1 or epsilon over 2a plus b plus 1. You need delta to be the minimum here because if epsilon over 2a plus b plus 1 is greater than 1, then this number will suffice. But this number might be too big. So you choose whichever of these is the smallest. So if if you're inside a neighborhood of radius 1, then this will be the limit this will be the expression that you want for delta in terms of epsilon. Okay, so let's do the proof then. Okay, so let epsilon greater than 0. Choose delta less than minimum 1 epsilon 2 over 2a plus b plus 1. Then if 0 less than absolute x minus a less than delta less than 1, then the absolute value, absolute value f of x minus L, right? Absolute x squared plus bx plus c minus a squared plus ba plus c. when you simplify, it gives you absolute value x minus a times absolute x plus a plus b, and that's less than absolute 2a plus b plus 1 times delta, and we chose delta to be less than epsilon over absolute 2a plus b plus 1, so when you multiply that by 2a plus b plus 1 in absolute value, you get epsilon, and that shows that the definition for the limit is satisfied. All right, and that's essentially the proof for that example. This is another example he does in the beginning of the chapter, so I wanted to do this with the formal definition. So here we want to show that the limit as x goes to 0 of x sine 1 over x is equal to 0. So again, start with your scratch work. So here I want absolute value x times sine of 1 over x to be less than epsilon. So here I can factor this into absolute value x times absolute value sine of 1 over x. But this is nice because the absolute value of sine of anything is always less than 1. So this product here will always be less than absolute value x. So I'll choose that to be less than delta, and I'll choose delta to be less than epsilon, and that'll work. So again, once you have delta, you're pretty much done. So let epsilon, here's the proof. Let epsilon be greater than 0. Choose delta less than epsilon. If 0 less than absolute x less than delta, then absolute value x times sine of 1 over x is equal to absolute value x times absolute value sine 1 over x, which is less than or equal to absolute value x, which is less than delta, which is less than epsilon, and that shows that the definition is satisfied. So that proves that the limit is 0. Right, and there's a similar example that he does next as well. Instead of x times sine of 1 over x, he does x squared times sine of 1 over x. We want to show that as x goes to 0, that's limit is equal to 0. So, similar thing. The only difference here is that when you do the work, you'll see that delta has to be less than square root of epsilon. So if you choose delta to be less than square root of epsilon, then you just go through the proof and you see that it works. So I won't go through the details here because it's so similar to the previous one. But you could pause the screen and look at the work here if you want to. All right. Now we get to some slightly different ones that are more complicated. Here we want to show that limit x goes to 0 sine of 1 over x does not exist. So here the limit does not exist. So in order to do this, I'm going to do a proof by contradiction. All right, so here's the proof. And like I said, he doesn't actually do this in the book. He sort of outlines how it's going to work, because he does this. He talks about this function before he does the formal definition. So here I'm just formalizing kind of like what he was saying. So here's my proof. So assume limit x goes to 0, sine 1 over x equals L, a real number L. Then for epsilon equals 1/2, for example, there exists a delta greater than 0, such that for any 0 less than absolute x less than delta, the absolute value of sine 1 over x minus L in absolute value is less than epsilon, which is 1/2. So we're assuming that the limit exists, in other words. So if the limit exists, then you should be able to get within a distance of 1/2 of L, right, by just taking x sufficiently close to 0. So let's assume that let's say I broke this into two cases. Assume L is positive or 0. All right, then we can choose n large enough. So that's what this notation means. N is very large, large positive. So choose n large enough so that the value x0 equals 1 over 3 pi over 2 plus 2n pi is less than delta. Okay, then if you take sine of that value, sine of 1 over x0 minus L, sine of 1 over x0, if you plug it in and simplify, that will always give you -1. So you get absolute value -1 minus L at that x value, which is the same thing as 1 plus L, right? You can just factor out the minus and then take the absolute value. And notice this is greater than 1/2, which is the epsilon we chose. So that's a contradiction, right? So that means that L greater than or equal to 0 can't be the limit. Well, maybe then that means that L is negative then. So let's try that. So if this is case 2, if L is less than 0, then choose n large enough so that x, here I'm calling it x1 to just distinguish it from x0. x1 equals 1 over pi over 2 plus 2n pi. Choose n large enough so that's less than delta. Then sine of 1 over x1 minus L is absolute value of 1 minus L in absolute value. That's when you simplify, that's equal to 1 plus absolute value L, because L is negative. We assumed L was negative here, right? So negative L is positive. So 1 plus absolute value L, that's obviously greater than a half. And that's a contradiction. And since we've exhausted all the possibilities for L, that means there is no limit. So this function here does not have a limit at 0. The limit doesn't exist at 0. Okay. Then he does this one he doesn't actually do in the book, but he says you should show this one yourself. So he says this one has limit at 0 but nowhere else, so you should prove it. So that's what I did here. So this is kind of an interesting function. Sorry, let me just readjust here. This futon is not the most comfortable place to sit, but this is the only room that I can do this in that has air conditioning, so it's just what it is. Okay, so f of x is the function. We're defining it piecewise. It's equal to x if x is rational, and it's equal to 0 if x is irrational. And we want to show that the limit as x goes to 0 of f of x is 0. So here's my scratch work. So if we take f of x minus L, in this case, that would be f of x minus 0, which would just give you the absolute value of f of x. But here, f of x is 0 if x is irrational, and x if x is rational. So the biggest this could be would be, x, right? Whatever x is. So that simplifies to absolute value x. I want that to be less than delta, which I can choose to be less than epsilon. So I'll choose delta less than epsilon. Okay, and then just do the proof. So let epsilon greater than 0, choose delta less than epsilon. If 0 less than absolute x less than delta, then absolute value f of x minus 0 is less than or equal to absolute value x is less than delta, which is, whoops, this should be less than epsilon, which is shows that the definition is satisfied. So that shows that the limit is 0 at 0. And then just to note, this is the only limit that exists for that function. This function has limit nowhere else, though. Like, if you approach any other value other than 0, then the function doesn't have a limit. So if you graphed it, it's a hard function to graph because of the way that the domain is broken up. But you have, the points lie along the line y equals x if x is rational, and it's 0 for all irrational values. So you get it looks like a bunch of points. Basically, it's impossible to draw by hand because there's uncountably many irrational numbers. But it it kind of, you could get the idea of kind of what it looks like by this picture. So clearly, if you approach 0, the limit is going to be 0, but anywhere else, the limit isn't going to exist because of the density of the rationals in the real numbers. So this is the only limit for that function that exists. Okay, here's another proof using the negation, I guess. Show limit x goes to 0 of absolute x over x. Show that limit doesn't exist. Again, this is one that he doesn't do in the book, or does he? I think he might talk about this function, but he doesn't. It was, again, before he does the formal definition. This function, if you can write this in a piecewise way, it looks like this: 1 if x greater than 0, and -1 if x less than 0. It's not defined at 0. So we want to show that the limit here as x goes to 0 doesn't exist. So again, I'm going to do this by contradiction. Here's the proof. Assume that limit as x goes to 0, absolute x over x is equal to L and R. Then for example, epsilon equals a half, there exists delta greater than 0, such that for all x with 0 less than absolute x less than delta, you should be able to have absolute x over x minus L and absolute value less than epsilon. Right here, we chose epsilon to be a half. So again, we'll do this in two cases. So case 1, assume L is greater than or equal to 0. Then we can choose x equal negative delta over 2. Clearly, that's less than delta in magnitude, so that would be in the interval from negative delta to delta. And if I plug that in for x into the function, then we get again, absolute value -1 minus L, which is 1 plus L, which is greater than 1/2, which is the epsilon that we chose. So that doesn't work. Case number two, sorry, I wrote case 1 twice. This should be case 2. All right, case 2 again would be the the complement of L greater than or equal to 0, which is L less than 0. So choose X equal to delta over 2. Again, delta over 2 is less than delta in magnitude, so that's inside the interval from negative delta to delta. Then if you plug that in for X into the function, you get absolute value delta over delta minus L in absolute value. That when you simplify that, you get absolute value 1 minus L, which is 1 plus absolute value L, because L is negative, which again is a number that's greater than 1/2. So that doesn't work either. And since that exhausts all the possibilities for L, that's a contradiction, because we assume that the limit exists, therefore the limit doesn't exist. So this limit as X goes to 0 of this function doesn't exist. Okay, so that's using the definition and a proof by contradiction, I guess, to show that this thing doesn't exist. Okay, and then he has a bunch of theorems, important theorems, that we'll use that we can use for limits to make taking limits easier than actually doing epsilon delta proofs. So theorem 1 is a property of limits. So let me just read it out and then we'll prove it. Theorem 1 says a function cannot approach two different limits near A. In other words, if f approaches L near A and f approaches M near A, then L equals M. Right. So if the limit exists, it's a single number. You can't have a limit of a function equaling two different values. That's what the theorem says. So let's prove it. Here's the proof. So let limit x goes to A of f of x equal L, and limit x goes to A of f of x equal M. Then for epsilon, here I'm choosing a specific epsilon equal absolute value L minus M over 2. I should maybe say here at the beginning, let this be true and assume. So why is this not writing? Oh, sorry, my computer does this sometimes. It's frozen for a second. Hopefully the video is still going though. Okay, sorry about that. So I should say here and assume L not M, because I'm going to do this by contradiction. Then for epsilon equal absolute value L minus M over 2, there exists delta 1, delta 2, so, greater, I should have greater than 0, such that absolute value f of x minus L less than epsilon, and absolute value g of x minus m is less than epsilon. Then we can choose delta to be the minimum of delta 1, delta 2. Then for any 0 less than absolute x minus a less than delta, if you look at absolute value L minus M, that's equal to absolute value L minus f of x plus f of x minus M. So here this has the same value because it's just like I'm adding 0. That doesn't change anything. But then I can use the triangle inequality, which is a theorem that we proved way back in chapter 1. This sum will be less than or equal to this absolute value x f of x minus L plus absolute value f of x minus M, which is less than 2 epsilon, right? Epsilon plus epsilon, which is equal to L minus M because we chose epsilon to be absolute L minus M over 2. And that's a contradiction because the number can't be strictly less than itself. All right, so that shows that the limit can't approach two different values. If it approaches L and M, then L has to equal M. All right, that's theorem 1. Okay, and then there's a theorem 2, but we need these 3 lemmas in order to prove the theorem 2. So let's go through. There's 3 of them, so we'll go through lemma 1, 2, and 3 before we do theorem 2. So here's lemma 1. If absolute value x minus x0 less than epsilon over 2, and absolute value y minus y0 less than epsilon over 2, then absolute value x minus y minus, in parentheses, x0 plus y0 is less than epsilon. All right, so let's prove that. So here, if you take absolute value x plus y minus, in parentheses, x0 plus y0. I just realized I'm missing a parentheses here. There should be an extra parentheses. And if you just rearrange things there, that's the same thing as absolute value of x minus x0 plus y minus y0. And by the triangle inequality, that's less than or equal to absolute value of x minus x0 plus absolute value y minus y0. And both of those are less than epsilon over 2, so you get less than epsilon over 2 plus epsilon over 2, which obviously is epsilon, so that proves the lemma. Right? There's a similar idea for lemma 2. So lemma 2 says if absolute value x minus x0 is less than minimum 1 or epsilon over 2 times absolute value y0 plus 1, and absolute y minus y0 less than epsilon over 2 times, in parentheses, absolute value x0 plus 1, then absolute value xy minus x0 y0 is less than epsilon. Right? So let's go through the proof. Okay, so if absolute value x minus x0 is less than 1, then by a version of the triangle inequality, that means that absolute value x minus absolute value x0 is less than absolute value x minus x0, which is less than 1, which means that absolute value of x is less than 1 plus absolute value x0. Again, you could see the proofs of the triangle inequalities if you go back to the videos from chapter, I think we proved it in chapter 1. If not, it's chapter 2, but you could go back and look. Okay, and then using that fact, then absolute value xy minus x0 y0 is equal to absolute value xy minus xy0 plus xy0 minus x0 y0. Again, these are equal because it's basically like I added 0 here. That doesn't change anything. Okay, and just rearranging some things here, factoring by grouping. So this is x times y minus y0 plus y0 times x minus x0. And then by the triangle inequality and properties of absolute value, that's less than or equal to absolute value x times absolute value y minus y0 plus absolute value y0 times absolute value x minus x0. And by what we assumed, that's less than 1, absolute value x is less than 1 plus absolute value x0, and y minus y0 and absolute value is less than epsilon over 2 times absolute x0 plus 1. Plus, and then, all those inequalities follow, right? I think I've said absolute value like 1,000 times already in this video. And then, so here, this cancels with this, and y0 over this is less than 1, which means that here you get, this just simplifies to give you epsilon over 2, and this is less than epsilon over 2. So epsilon over 2 plus epsilon over 2 simplifies to give you epsilon, and that proves the lemma. Okay, lemma 3. If y0, this is the statement. So if y0 is not 0 and absolute value y minus y0 is less than minimum of absolute value y0 over 2, or epsilon times y0 squared over 2, then y is not 0, and absolute value 1 over y minus 1 over y0 is less than epsilon. Okay, here's the proof. So since absolute value y minus y0 is less than absolute value y0 over 2, that implies that negative absolute y0 over 2 is less than absolute y minus absolute y, absolute value y0. Again, that's by triangle inequality. And that's less than absolute value y0 over 2. What I'm trying to say is this, just so it's not confusing, this is less than this by the triangle inequality is what I'm trying to say. And since this thing is bounded above by this, actually it should be absolute value of this is less than that. Then you can just use the compound inequality to break it up into a triple inequality. Okay, and then here, if you add absolute value y0 to both sides, then you get that 0 is greater than absolute y0 over 2, less than absolute value y, which shows that y is bounded away from 0. So that shows this part, right? Y is not 0. That implies that 1 over absolute value y is less than 2 over absolute value y0 when you flip the inequality over. or take the reciprocals of both sides, right? The inequality switches direction. Then that means that absolute value of 1 over y minus 1 over y0 is equal to, when you simplify, absolute value y minus y0 over absolute y times absolute y0. And we know that the 1 over absolute value y is less than 2 over absolute value y0 times this extra y, absolute value y0, gives you the factor of 2 over absolute value y0 squared, and the y minus y0 in absolute value is less than this expression here by our assumption. So when you simplify everything here, notice that the 2's cancel and the y0 squareds cancel, so you're just left with epsilon. So that shows that the limit is that shows that the property holds. All right, so with these lemmas, now we can prove theorem 2, which I'll show you right now. Okay, theorem 2 says if limit f of x equals L as x approaches A and limit g of x as x approaches A is equal to M, then there's three things. So for number one, if you take the sum of f and g if you take the limit as x approaches A of the sum f plus g of x, that's equal to L plus M. Then part 2 says limit x goes to A of f times g of x is equal to L times M. And part 3 says limit x goes to A of 1 over g of x is 1 over m, provided that m is not 0, because division by 0 is not defined. So what this is saying is the limit of a sum is the sum of the limits, and the limit of a product is the product of the limits, and the quotient of, or the reciprocal, I guess here is the way that it's stated. The reciprocal of a limit is the reciprocal of the limit. So again, provided that the limit of g is not 0. All right, so let's prove those. We're going to use those lemmas in order to do this, to prove these parts. So I numbered them. This is the proof for 1, 2, and 3. So so here's the proof for 1. All right, so assume that limit x goes to A of f of x is L and limit x goes to A of g of x equals M. And if that's true, that implies that for any epsilon greater than 0, we can find delta 1, delta 2 greater than 0, such that if 0 is less than absolute x minus A, less than delta j. So here I'm just writing this, because there's two deltas here, I'm just writing this delta j, meaning, this holds for j equals 1 or 2. Then if I choose delta to be the minimum of these two things, and if 0 is less than absolute value A, x minus A less than delta, which is I'm defining here, then absolute value f of x minus L is less than epsilon over 2, and I can make it less than epsilon over 2, and absolute value g of x minus m is less than epsilon over 2. And if I look at the limit of f of x plus g of x minus, sorry, not the limit, if I look at the absolute value of f of x plus g of x minus L plus m, and rearrange things, that's equal to absolute value f of x minus L plus g of x minus m. And then using the triangle inequality, that's less than or equal to absolute value f of x minus L plus absolute value g of x minus m, and that's less than epsilon over 2 plus epsilon over 2, which is equal to epsilon, and therefore that shows that the limit of the sum is the sum of the limits. All right, so that's the first part. Here's the proof of the second part. And like you can see that we're relying here on those lemmas. So this, this follows from lemma 1. And for 2, we're going to rely on the fact that lemma 2 is true, and for 3, we're going to rely on the fact that lemma 3 is true. Okay. So for part 2, for any epsilon greater than 0, we can find delta 1, delta 2 greater than 0, such that for 0 less than absolute value x minus A less than delta j. Again, here, I'm just writing it compactly like that. J, j stands for 1 or 2. Absolute value f of x minus L is less than minimum of 1 or epsilon over 2 times absolute value m plus 1, and absolute value g of x minus m less than epsilon over 2 times absolute value L plus 1. Then choose delta equal minimum, delta 1, delta 2. That implies that absolute value f of x g of x minus Lm is equal to absolute value f of x g of x minus f of x m plus f of x m, so minus Lm. Again, this is equal because it's like I added 0 here, right? This sums to 0. And that's by the triangle inequality and properties of absolute values. That's less than or equal to absolute value f of x times absolute value g of x minus m plus absolute value m times absolute value f of x minus L. And which is less than 1 plus absolute value L times epsilon over 2 times, in parentheses, absolute value L plus 1 plus absolute value M epsilon over 2 times absolute value M plus 1. So here, notice that these cancel, so you get epsilon over 2. And then again here, M divided by absolute M plus absolute value M divided by absolute value M plus 1 is less than 1. So this expression here is less than epsilon over 2, and epsilon over 2 plus epsilon over 2 is equal to epsilon. So that shows that property 2 holds. So the limit of a product is the product of the limits. Right. Number 3, property 3, here's the proof. For any epsilon greater than 0, we can find delta greater than 0 such that 0 less than absolute value x minus a less than delta. That implies that absolute value g of x minus m less than minimum absolute m over 2, comma, epsilon m squared over 2. Again, this is from lemma 3. Then for any x, 0 less than absolute x minus a less than delta, that implies that absolute value 1 over g of x minus 1 over m is, when you simplify, is equal to absolute value g of x minus m over absolute g of x times absolute value of m, and that's less than 2 over m squared times epsilon m squared over 2. And again here, if you notice, all the important stuff cancels, so you're just left with epsilon, which shows that property 3 holds. Right, and that's the proof for theorem 2. So now we have these properties of limits that we can use, which will be useful, because then now that we know that these hold for any functions for which the limits exist, and for the reciprocal, the limit can't be 0, but for for functions that satisfy those conditions, we can use these properties, which means we don't have to do an epsilon delta argument, which is very tedious and time consuming. So that's nice. We have that theorem now. And then lastly, he ends with a few extra definitions. So he doesn't really do much in the chapter itself with these definitions, but he says that we'll do something with them in the exercise set. So like I said, there's a lot of exercises for this section. So let me just read some of them out. The first 2 definitions that I have here are for one-sided limits. The first definition is for the limit as x approaches a from above. So limit x goes to a from above, f of x equals L, means for any epsilon greater than 0, there exists delta greater than 0, such that for all x, such that 0 less than x minus a less than delta implies absolute f of x minus L less than epsilon. So here, we're approaching x through positive, we're approaching a through positive values, so values that are bigger than a, which means that this difference will always be positive, so you don't need the absolute value, in other words. So you want to you're only considering a portion of the domain where the x values are greater than a for that one-sided limit. And then there's a similar definition for the limit coming from below. So the limit x goes to a from below of f of x equals L means for every epsilon greater than 0, there exists a delta greater than 0, such that for all x, such that 0 less than a minus x, again, notice that's positive because x is less than a, less than delta, for all x that satisfy that inequality, absolute value f of x minus L is less than epsilon. So that's the definition, the formal definition for the one-sided limit coming from the left or from below. Right, and then he also gives another definition for an infinite limit. There's a whole bunch of them that, because it's a lot of different cases. So he doesn't go all over every single definition in the chapter, but you should be able to derive them yourself if you understand the concept now. And he does say that he goes over some more definitions in the exercises themselves. So I guess we'll see some of those definitions there. But like, for example, you should be able to come up with the definition for the limit of a function blowing up at a point, for example. Maybe I'll do that for you. I'll write that down here in addition to this, but this is the last definition that he actually gives in the book. Sorry, not in the book, but in the chapter 5. So this is for the limit as x goes to infinity. So limit x goes to infinity of f of x equals L means for any epsilon greater than 0, there exists n greater than 0, such that for all x greater than n, absolute value f of x minus L less than epsilon. Right, so that's the last thing in the section. Maybe just so you can see what I was talking about before. Here's another definition. Well, this is what I mean. Like, if you understand the concept, you should be able to just write down what the definition is for all the other cases that can happen. For example, let's say that we have a function that is not that blows up to infinity at a point. So let's say the limit as x approaches a of f of x equals infinity. Let's say. So this would mean for let's see, so for any m greater than 0, there exists delta sorry, I shouldn't be using symbols here. I'll write this out in English. There exists delta greater than 0 such that for any 0 less than x minus a less than delta, f of x greater than m. Right, so that would be the definition for that infinite limit there. And there's a bunch of other cases that can happen. So it's just too many to like just write out completely. But like I said, if you understand the concept, just seeing those previous definitions, you should be able to come up with the definitions for all the other cases yourself. All right, so let me just stop the screen share for a second. That was kind of a long chapter, like I said. But I hope you guys enjoyed the video. I will be doing the exercise sets for these soon, so keep an eye out for that. Tomorrow, I think, though, I'm going to be working on the exercise sets tomorrow, but like I said, there's a lot of them, so I'm probably not going to be able to post a video for that tomorrow. But I do plan on posting so section 2.1 or 2A rather, I'm going to do in linear algebra done right. And also I want to finish up chapter 1 in multivariable mathematics. So I might do, actually tomorrow, I think I might do, what section are we up to in here? Because it's been so long. We're up to chapter 1, section 4. So I'm going to do that one tomorrow. I think that's what I'm going to shoot for. I'm going to do this chapter summary for chapter 1, section 4 in Schifrin. And then the day after that, I'll do the summary for 2A in Axler, and then hopefully I'll be able to post the exercise sets for those in the following days. So again, thanks for watching, guys. Check out the Patreon page. I'll leave a link to it in the description if you want to support the channel. It costs $5 a month, and you do get additional content. So check it out and see if you're interested. And keep an eye out for the video tomorrow. Like I said, I'll be posting videos every day for the next couple of weeks at least. So I'll see you guys then. Until that time, keep learning.